Welcome back to the deep dive. So, if you've ever found yourself wondering what actually powers the biggest applications on the planet, the ones managing just insane amounts of data without even breaking a sweat, you are definitely in the right place.
Yeah, we're going to try and cut through some of the noise today.
We're going for the ultimate shortcut to understanding really the bedrock of modern cloud architecture, Google Cloud Storage.
And, this deep dive isn't just about storage. It's really a mission brief on how massive digital applications work at their most basic level, GCS or Google Cloud Storage. It's the essential layer. It's kind of like the engine oil in the whole digital machine.
Right. And our mission is to boil down a huge stack of material so that you, our learner, can walk away with a really solid grasp of GCS's role. It's this critical, hugely scalable storage layer.
It's what lets organizations scale globally in, milliseconds?
Yeah.
Instead of weeks or months.
Exactly. So let's establish its core identity right away.
Okay, so the official definition is it's an enterprise-grade, highly scalable and durable object storage service. But, that's a bit clinical. That definition really hides the true magnitude of what it does.
It does. Let's focus on that word scalability, because when we say GCS can handle virtually any amount of data, that's not an exaggeration, is it?
Not at all. We're talking about one single service that can handle everything from the tiniest little log files to, these massive archival data sets.
So it could be high-frequency website content 1 minute, and then long-term, cold archival data you might touch once a decade the next.
Yeah, and it's really the backbone of the entire Google Cloud Platform ecosystem. If you think of GCP as this high-throughput digital factory, GCS is the warehouse. It's infinitely deep, it's resilient, and it's always stocked with raw material.
It's the fuel for compute engines, for machine learning models like Vertex AI, for these big data pipelines.
Right. The ones analyzing everything from user behavior to climate patterns, it all sits on GCS.
And this, I think, brings us to the fundamental conceptual leap. The thing that changes everything for how a company plans its infrastructure and its finances. GCS completely abstracts the physical hardware away.
That's the key. You are no longer buying servers, you're not dealing with disk failures or worrying about RAID arrays or even data center cooling. It's all gone.
That physical abstraction, that's the real key to agility, isn't it?
It is. Instead of fighting with physical limits or, getting CapEx budgets approved for more storage, GCS lets organizations treat storage as an infinite programmable resource.
That's a total paradigm shift.
It is. You move your focus from managing infrastructure to just programmatically managing your data. And that shift is, I would argue, the single biggest change cloud computing delivered.
So if your storage is infinite and programmable, that means the speed you can launch a new service is no longer limited by a procurement process. Okay, let's unpack that programmable architecture. We'll start with section 1. Before we can really get what makes GCS unique, we have to place it in the larger world of cloud storage. We need to look at the 3 main paradigms in Google Cloud.
Yeah, that context is so important. People just throw around the phrase cloud storage, but the reality is that different jobs need radically different tools. You wouldn't use a scooter to haul a semi-truck's load.
Or a semi-truck for a quick errand. Okay, so let's start with the one that's most familiar to anyone who's ever owned a computer. Block storage. In GCP, that's persistent disk.
Right. Block storage is it's the high-performance workhorse. Think of it as the direct digital equivalent of attaching a raw physical hard drive to one of your virtual machines.
So it shows up to the operating system like a raw disk.
Exactly.
Yeah.
Which means it has to be formatted by the OS, with file systems like ext4 on Linux or NTFS on Windows, before you can even use it.
And that's where the performance comes from, right? Being so close to the machine.
Precisely. It's locally attached, or at least appears to be, which gives you extremely high throughput, and then this is critical, very low latency. It's perfect for things like boot disks, obviously, but really for transactional databases that need tens of thousands of IOPS, input-output operations per second.
Okay, so like a database processing a ton of financial transactions, it needs that instant guaranteed low latency confirmation.
That's the sweet spot for block storage.
Okay, moving on. The second pillar, file storage or file store. So if block storage is like a private hard drive, what's file storage?
File storage, it fills the gap that block storage leaves. It's essentially a managed network attached storage service, a NAS. The big difference here is the protocol it uses. It supports NFS.
And that gives it shared file system semantics. Why is that important?
because it lets multiple virtual machines, maybe dozens of them, all mount the exact same file system at the same time.
Oh, I see.
So if you have, say, 5 application servers that all need to read and write to the same set of configuration files or media assets, they can all just access that same central location. It's totally transparent to them.
Okay. So this is less about raw single machine speed and more about providing a familiar environment for apps that were built assuming they'd be on a shared network drive.
You got it. It makes migrating those legacy applications, the ones designed for a typical Office network, much, much easier. You don't have to re-architect them from scratch.
Which is a huge cost saver.
A lifesaver for many companies.
All right, now we get to the third pillar, the real focus of our deep dive, object storage, which is GCS. So
Yeah.
if block is the hard drive and file is the network folder, what on earth is object storage?
This is where we break from tradition. We're now in the world of true web-scale computing. Here, data is stored as individual, discrete objects. You have to forget about the files and folders you've known your whole life.
The whole organization is different.
And the access method is radically different.
Oh, so
You don't mount a drive and access it with a file path. Access is purely through an API, specifically HTTP pressed. You're basically interacting with your data the same way your web browser interacts with a website, using standard web calls like get, put, and delete.
I like that. It's like calling a concierge service to get something for you instead of walking to the shelf yourself. And if I'm making a web call, I can get that data from any device anywhere in the world without worrying about mounting or formatting. That's the key for global reach, isn't it?
It absolutely is. And the benefits that come from this API-driven, object-based architecture are just transformative. You get practically limitless scalability, you never have to think about capacity, and it's typically the lowest cost per gigabyte at scale compared to the other two.
Okay, let's go deeper into that architecture now. Section 1.2, the anatomy of a GCS object. This idea of a flat namespace is so important to get right because it's completely counterintuitive.
It is the hardest concept for people to get their heads around. We call it a flat namespace, which means even though you might look at an object's name and see something like logs 2023 October error log.txt, which looks like folders.
The slashes are just for show.
Exactly. They're purely cosmetic for our human convenience. They're just prefixes. Fundamentally, every single object exists at the same logical level inside its container, which we call a bucket.
So it's like one enormous planetary scale spreadsheet. Every row is an object, and the name, including the slashes, is just the unique text in one of the columns.
That's a great analogy. You don't actually navigate a nested tree. You just query the flat list based on that text prefix.
So the search engine doesn't have to walk through shelves. It just scans the full list of barcodes instantly.
That's the strategic advantage. Now let's break down the 3 main components of every object. The first one is the easiest, the data.
The payload, the content itself, an image, a video file, a CSV, a JSON file, anything.
All right. Second, we have the key, or the object name. As we said, this is the unique identifier string within that bucket. That logs 2023 October error log.txt example. It has to be unique.
And the third part, which really elevates GCS from just being storage to being a programmable resource, is the metadata.
Metadata is where all the magic happens. And we can break this down into 2 types. First, you have system metadata, which GCS generates and manages automatically for you.
Right. This is stuff like the size of the objects, the created date, the content type, and those all-important integrity checks, the checksums.
Yes, the CRC3D2C checksum, or the older MD5 hash. And speaking of integrity checks, this is a little detail that really shows Google's commitment to reliability. GCP strongly prefers the CRC3D2C checksum.
And why is that specific checksum important for us to know?
Well, the C stands for Castagnoli. It's a specific version of CRC that's designed to be computationally cheap. This is the key. It's often accelerated directly in the hardware of Google's data center. So it means GCS can verify the integrity of an object during transmission or retrieval incredibly fast. It gives you super high confidence that the bits you stored are the exact bits you're getting back, all without slowing down your high throughput pipelines.
That's efficiency married to absolute durability. That is deep dive material. Okay, what about the second type of metadata?
The second flavor is custom metadata. This is the truly programmable part. It lets you, the user, define your own arbitrary tags. You can add things like project, Apollo, or data sensitivity, confidential, or status. reviewed.
The power there is for organization. If I have a million objects and I want to find everything related to Project Apollo, I don't need to know the file path, I just query the tag.
Exactly. It shifts the burden away from creating these complex nested folder structures, which always break down over time, and moves it to high-speed programmatic querying. You tag your data, and it instantly becomes searchable on multiple dimensions at once.
Which is a perfect transition to seeing this in action. Let's move to section 2. Real-world applications and massive-scale use cases. We're going to look at 3 very different scenarios. Let's start with media production and archiving.
The challenge in media is just the sheer scale and the longevity of the data. Imagine a major production house shooting a movie, generating petabytes of raw 8K video footage. In the old world, that meant building these huge, complex storage area networks, SANs, or massive NAS arrays.
Right, which are just infrastructure nightmares. You're constantly worried about heat, power, data migrations every few years, and the huge upfront capital expense, the CapEx.
The GCS solution just cuts that cord completely. When a project is done, the studio doesn't have to keep that cold, inactive footage on expensive high-speed disks. They can move it straight into archive storage.
Which we'll talk about later, but it's the lowest cost storage class.
It is. So they drastically cut their monthly storage bill for assets they aren't actively using.
And what about the active project files, the ones editors are working on right now?
Those stay in standard storage, where access is fast. And because GCS is software-defined, they can find and retrieve millions of video clips, audio tracks, whatever, just by using those intelligent metadata tags and naming prefixes we talked about. It's an instant, programmable library, not a physical warehouse they have to staff and maintain.
That segmentation makes a ton of sense. Okay, next up, a critical one for business survival, global asset hosting for e-commerce. Latency isn't just an annoyance here, it's a direct sales killer.
Oh, absolutely. Study after study shows that every fraction of a second you add to page load time, your conversion rate drops. So imagine an e-commerce giant serving product images and thumbnails to millions of users at the same time, all over the world, say, in Mumbai, London, and San Francisco.
If they just stored everything in a single US region, the latency for the user in Mumbai would be painful, right?
Awful. The speed of light is a hard limit.
Yeah.
So to solve this, they use a really powerful GCS feature. Multi-regional or dual-region buckets. This automatically replicates their data, those product images, across geographically distant locations.
But hold on. Doesn't replicating data across continents massively increase your storage costs and complexity? What's the cost benefit here versus just using a single region with a cheaper CDN?
That is a great question. And yes, there is a higher cost for the replication, but what you gain is resilience and performance at a massive scale. A dual-region setup, for instance, puts your data in 2 very distant regions, which gives you incredible resilience against a regional outage.
Okay, so it's a disaster recovery benefit.
It is, but more importantly for performance, it ensures your data is physically closer to the endpoints of Google's global network.
And that's where the cloud CDN integration becomes the final acceleration layer.
Precisely. The CDN is the finishing touch. It caches those replicated assets at the edge of Google's network in hundreds of locations worldwide. So the image might be served from a cache server that's just a few blocks from the customer's device. You pay a bit more for replication, but you get near-instant, highly reliable global delivery, which directly translates into more sales.
Shaving off those milliseconds creates a huge competitive moat. Okay, our third case study is all about compliance and security, healthcare AI training, and regulatory compliance. This is where data integrity has to be legally guaranteed.
Yeah, this is a very tough environment. Imagine a startup training a neural network on sensitive medical data, like anonymized MRI scans. They have to comply with regulations like ILAIA, which often say records cannot be altered or deleted for a set period, maybe 7 years.
So how does GCS provide that hard, immutable guarantee?
They store the scans as objects, of course, but then they enable a feature called bucket lock, which enforces retention policies. And this isn't just a soft warning label. Once you activate and lock it, it provides a hard regulatory guarantee. It prevents anyone, even the account administrators, from deleting or modifying those object versions until that retention period is up.
So if an auditor shows up, the company can mathematically prove that the data has been preserved in a write once, read many state. Its integrity is guaranteed.
That integrity is non-negotiable. It provides the legal protection they need. But crucially, once the data is secured in GCS, it's also immediately useful. The data scientists don't have to download it or copy it somewhere else.
They just point their tools at it.
They just point their Vertex AI training jobs directly to the GCS path. The training engine then ingests those petabytes of MRI files at incredibly high throughput directly from storage. It's vital for efficient machine learning.
That really shows GCS not just as a secure vault, but as an active, high-speed feeder for modern analytics. And that connection point leads us perfectly into Section 3, GCS as the glue in the GCP ecosystem.
Exactly. As powerful as GCS is by itself, its value just multiplies when you integrate it with other services. It's the connective tissue.
Okay, let's start with maybe the hottest topic in data architecture today, the big data lakehouse. We hear that term all the time. What is GCS's foundational role here?
Well, a data lakehouse basically tries to merge the low-cost, flexible storage of a data lake with the structure and query performance of a data warehouse. And GCS is the high-durability landing zone for all that raw, untransformed data. Every click, every log, every external data set, it lands in a GCS bucket first.
So GCS is the massive, infinitely scalable storage layer of the lakehouse.
It is. It holds everything. And this is where we get that big aha moment about efficiency, specifically with BigQuery.
You're talking about BigQuery's ability to do federated queries. For anyone who's not familiar, what does that actually mean?
It means BigQuery can use its massive computational power to analyze data that is sitting directly in GCS, as long as it's in an open format like Parquet or Avro, without you having to spend time and money importing or duplicating that huge data set into BigQuery's own storage first.
Wait, so you're telling me you don't even have to move the data? That seems like a revolutionary step in cost and time savings. You just bring the processing to the data.
That's it. You bring the compute to the data, not the other way around.
How does BigQuery manage to do that efficiently without actually owning the data?
It's incredibly smart.
Yeah.
Because the data is in a columnar format like Parquet, BigQuery doesn't have to read the entire file or object. It uses the metadata inside the Parquet file to only read the specific columns it needs to answer your query.
Wow.
It's a highly optimized read directly from GCS over the API, so you can leave vast archives in GCS, which is way cheaper than BigQuery storage, and only pay the BigQuery compute cost when you actually run a query on it.
That's huge. That massively lowers the barrier to querying historical data. Okay, moving beyond big analytics, let's look at GCS's role in event-driven architectures, serverless automation, and triggers.
This really shows how GCS can be an active trigger, not just a static box. It's all about reacting instantly to change. It can generate an immediate, reliable notification and event whenever a specific action happens, like a new object being uploaded.
And once that event fires, where does it usually go?
Most commonly, it'll automatically trigger a serverless compute engine like a Cloud Function or a Cloud Run service.
Right, the classic example is media processing. Walk me through the exact steps.
Okay, a user uploads a high-res 10-megabyte photo to a specific incoming GCS bucket. The second that upload finishes successfully, GCS fires an event. That event instantly wakes up a pre-configured Cloud Function. The function runs a tiny snippet of code, we're talking milliseconds of runtime, that pulls the photo from GCS, creates a low-res 100-kilobyte thumbnail version, and then saves that thumbnail back into a different GCS bucket that's optimized for web surfing.
A fully automated, scalable workflow, and you only pay for storage and the fraction of a second the function runs. No idle servers.
That's the beauty of it. And of course, GCS is also fundamental for basic backup and recovery for other GCP services.
The ultimate safety net.
It's the simplest and most crucial role. Databases, whether it's Cloud SQL or a NoSQL database, or even the globally distributed spanner, they all routinely export their backups directly to GCS. It gives you durable, off-site storage that is decoupled, there's that word again, from the live database environment.
So if the database region has a problem, the backups are safe and sound somewhere else.
Exactly. And finally, making sure all that data is safe. Security integration.
Non-negotiable.
Right. Good. And GCS does this through incredibly tight integration with Cloud IAM identity and access management. This allows for very granular control over who can do what to which data. Granular is the key word.
So you're not just granting access to the whole account or even the whole bucket.
Absolutely not. You can enforce the principle of least privilege with extreme precision. You can grant a very specific role, like storage object viewer, to a person or an automated service account. So a machine learning model might be able to view the raw data for training, but it is explicitly forbidden from deleting or modifying it.
That separation of duties is essential for data governance and just preventing accidents.
Or malicious acts, yes.
Okay, that wraps up GCS's role as the central integrator. Let's get into Section 4 now, where we can explore some of the deeper, more technical concepts that really differentiate GCS. And we start with a heavy hitter, strong global consistency.
This is a huge technical differentiator. It's a critical feature for any high-stakes global application. GCS provides strong global consistency for all operations.
Okay, wait a minute. I mean, isn't achieving immediate global consistency a massive engineering challenge, especially when you're replicating data across continents? How does Google pull this off?
You're right, it is a massive challenge. And it's achieved by leveraging Google's foundational distributed database technologies like Colossus and Spanner, which are designed to enforce this kind of atomicity across the globe. When a write operation succeeds in GCS, the system guarantees it's been written atomically across all the relevant infrastructure.
So what does strong global consistency actually mean for me, the developer using GCS?
It means total reliability. If you upload a new object or overwrite an existing one, any subsequent read request from anywhere in the world milliseconds later is guaranteed to see the latest correct version. There's no ambiguity, no maybe.
And the alternative, which you see in some other systems, is eventual consistency. I know that can cause some real problems.
A huge headache. With eventual consistency, a write confirms success, but there might be a delay seconds, even minutes, before that change propagates globally. For applications that need immediate accuracy, like financial systems or logging pipelines, that delay can lead to serious errors or even data corruption.
So GCS removes that uncertainty. The engineers don't have to build complex workarounds to check if the data they just wrote is available yet.
They can just trust the storage layer implicitly. It's a really powerful, if understated, feature.
Okay, let's move to the second advanced concept, storage classes and cost optimization. When you're managing petabytes, your cost strategy is everything.
Right. And the core optimization strategy in GCS is simple and elegant. You trade access frequency for lower cost. The less you need the data, the cheaper it is to store.
But, and this is the catch we mentioned earlier, if the storage cost is low, the cost to retrieve it must be higher. Otherwise, everyone would just use the cheapest one.
That is the essential caveat. Retrieval costs absolutely apply to the non-standard classes, and that's the incentive to put your data in the right tier. Accidentally accessing your cold data too often can lead to a massive, unexpected bill.
I can imagine.
I've seen it happen. A company saves a fortune moving old backups to archive, but then accidentally points a frequently accessed dashboard at it. The CFO nearly fainted when the retrieval bill came in. You have to monitor those access patterns.
That's a great practical lesson. Okay, let's run through the 4 primary classes so we all know the trade-offs. Let's start with standard.
Standard is your baseline, your workhorse. It's for frequently accessed data-active applications, website assets, real-time data ingestion, minimal access latency, and crucially, 0 retrieval fees. This is your hot, active data.
Okay. Next down is nearline.
Nearline is the first step down in cost. It's best for data you access less than once a month. Think of things like monthly reports or operational backups you might restore once a quarter. You pay a lower monthly storage cost, but retrieval fees kick in.
Then we have Coldline.
Coldline takes the savings even further. This is for truly infrequent access, less than once per quarter. This is disaster recovery images, older backups, compliance data sets you have to keep but hope you never need. Storage is cheaper again, but retrieval costs and the minimum storage duration are higher.
And finally, the deepest, cheapest tier, archive.
Archive is the ultimate in low-cost storage. It's for data you access less than once a year. This is for your long-term regulatory archives or that media house's finished 8K footage. The storage cost is pennies. You hope you never have to touch it. Consequently, the retrieval costs are the highest, but if you truly stick to that access model, the savings are transformative.
So understanding your data's lifecycle and access pattern is the single biggest factor in managing cloud costs at scale.
It's all a strategic data governance.
Okay, let's move on to section 4.3 and look at 2 practical architectures that tie all of this together. First, let's revisit something simple but powerful, static website hosting.
Yeah, hosting a static site on GCS is incredibly cheap and performant. The process is pretty straightforward. You just upload your fixed content to your index.html, style.css, images, JavaScript directly to a bucket. That bucket is now your origin server.
But if the bucket is the origin, why do the guys always say to connect it to Cloud Load Balancing and Cloud CDN? If it's static, why do I need a load balancer?
That's a really important technical point. You need the load balancer not really for load distribution, the bucket can handle that just fine, but for features like custom domain mapping, so you can use www.yourcompany.com, and most importantly for SSL termination. The load balancer handles all the security, making sure your traffic is over HTTPS.
Got it. So CLB is for security and routing, and then Cloud CDN is for speed.
Exactly. CDN takes those files and caches them all over the world at the network edge. So when a user requests your homepage, the request hits the load balancer, which then directs to the nearest cached copy via the CDN. You get maximum speed, all without a single server or VM running your app.
An incredibly lean and robust setup. Okay, the second example is much more complex. An IoT data pipeline. This requires GCS to handle high volume and act as a checkpoint.
This is a classic three-stage flow for stream processing. GCS acts as the resilient landing pad.
Stage 1, ingestion.
Right. You've got thousands of IoT sensors out in the field sending readings continuously. That data first goes to Cloud PubSub, which is Google's scalable messaging service. PubSub acts as the buffer, handling the sheer volume and velocity of the incoming stream, making sure no data is lost.
So PubSub is the shock absorber. What's stage 2, processing?
This is where a service like Cloud Dataflow comes in. Dataflow is built to read that continuous stream from PubSub. It can clean the data, validate it, convert formats into, say, Avro or Parquet, and then, this is the crucial bit, it saves the clean, structured data into GCS in batches, maybe every 5 minutes or every hour.
So GCS becomes the reliable, durable checkpoint. It turns that chaotic, real-time stream into structured, queryable batches on disk.
Exactly. If Dataflow ever fails and needs to restart, it knows exactly where it left off because the data is safely checkpointed in GCS. And that leads to stage 3, analysis.
Where the business value comes out.
Right. Now, your analysts and data scientists can use a tool like BigQuery to run queries on those structured files sitting in GCS, remembering that federated query capability. They can look for anomalies, generate reports, train models. GCS is the pivot point that connects the real-time stream to the historical analytics engine.
That perfectly illustrates GCS not as a silo, but as this integrated persistence layer. Okay, let's wrap up with a powerful real-world example in Section 5, a case study on Spotify's data transformation.
Yeah, Spotify's story is the perfect example of the strategic power of object storage. It's all about that critical concept of decoupling storage from compute. They were very open about their migration from these huge, expensive on-premise Hadoop clusters to Google Cloud.
So what was the key problem with their old system?
In the traditional Hadoop architecture, the storage, the physical hard drives with all the listening logs, was intrinsically tied to the compute, the CPUs running the calculations.
So if you needed more compute, you had to buy more storage, even if you didn't need it.
That was the inherent flaw. If they needed more processing power for a few hours to run a complex model, they had to scale up the whole cluster, which meant buying and maintaining more physical hardware for both, even if their data volume was the same. The two were coupled.
Which makes elasticity basically impossible.
Correct. So when they migrated, GCS became their primary data lake. It housed all their massive data sets, listening logs, music metadata, user interactions, everything.
And the major architectural breakthrough they achieved was definitively decoupling their storage from their compute.
That gave them unbelievable elasticity and cost control. So if they need to run a massive job, like calculating everyone's personalized Spotify Wrapped at the end of the year.
Which is a huge but temporary job.
Exactly. They can spin up thousands of virtual CPUs using services like Dataflow or Dataproc for just a few hours.
And because the data is just sitting in GCS, spinning up those CPUs doesn't require buying a single extra hard drive. They pay for the compute for the few hours they need it, and then they just shut it down.
And the reverse is true. If their storage needs grow massively because they enter a new market, they don't have to spin up any extra compute just to support that storage growth. Yeah. That radical elasticity is the core strategic benefit of the GCS paradigm.
A tremendous illustration of how this enables real business agility. Okay, let's bring it all back together. A quick summary of the critical takeaways from this deep dive.
Well, we established that GCS is this unique, flat, object-based storage system built for durability and massive global scale. And we defined its difference from block and file storage, noting it's all API-driven.
We also looked at its role as a system integrator, how it seamlessly connects to BigQuery for querying in place, Cloud Functions for serverless automation, and CDN for global delivery. You need that to build modern apps.
And finally, we covered the key technical and cost strategies, the guarantee of strong global consistency for reliability, and the strategic trade-offs of the 4 storage classes for managing petabyte-scale budgets.
So we've gone from the basic definition of a digital object all the way to its use in a global music platform. Now it's time for our final provocative thought for you, the learner.
We spent a lot of time on the power of custom metadata versus traditional rigid folder structures. It's what turns storage into a programmable asset.
Right. So if you were designing that healthcare app again, the one storing MRI scans and patient records, how would using, say, 3 custom metadata tags, instead of just relying on folders, immediately help a doctor find a specific patient record faster and more efficiently?
Think about it. A traditional folder structure forces a file into one place. You file a scan under patient ID MRI scans, you can really only find it easily by patient ID. But what if the doctor only remembers the date range and the procedure type?
Yeah, they'd have to click through every single folder. But with GCS, you could define 3 tags. What would those 3 tags be?
Well, maybe the first is patient ID. The second could be scan type like MRI, XRAY, ultrasound. And the third could be review status pending, finalized, Cento Insurance.
So then the doctor can instantly query the entire database by asking, show me all pending MRI scans for patient ID 456.
And retrieve that exact object in milliseconds, regardless of where it's filed.
That ability to query data on multiple axes at once, that flexible organization,
Okay, yeah.
that's the strategic value of the object storage paradigm over old school file systems. A powerful thought to leave you with.
We hope this gave you the foundational knowledge you need to really understand these massive architectures.
That's all the time we have for this deep dive into Google Cloud Storage. Thanks so much for joining us.
Until next time.